Hi, my name is Paul Yip, and I'm the product manager for Big Insights. I'm going to talk to you today about Spectrum Scale fundamentals for Hadoop practitioners. So this presentation makes an assumption that you know Hadoop and HDFS, and the objective of this presentation is to help map those skills and those terms over from HDFS world to GPFS. Now, first and foremost, you may know Spectrum Scale already as GPFS. So from a naming perspective, I may refer to GPFS, I may refer to Spectrum Scale, but they both are going to mean the same thing. And sometimes we may refer to the term FPO. I'm going to talk about what that means. The equivalent then of GPFS FPO is going to be Spectrum Scale FPO. It should be noted that GPFS and GPFS FPO, they're the same code base. It's just a different topology. Traditionally, GPFS has used a shared disk architecture for its files. However, with the introduction of big data and Hadoop, GPFS started to support this alternative topology where the disks are spread across a number of nodes using just a bunch of disks. And so FPO stands for File Placement Optimizer. In this presentation, you're going to find that I'm going to use GPFS a lot instead of Spectrum Scale. This is simply because old habits die hard, and I find it easier to say, so let's begin. The first term I'll cover to compare HDFS and GPFS is the term block. In Hadoop, when I write a large file, that file is broken up into many blocks. And this block is typically in the range of 64 megabytes to 128 megabytes. And the reason for this is to reduce the amount of entries I need in the name node to represent that file. Now, GPFS also has a term block, which is actually different. And this is because GPFS has existed long before HDFS. So I want to call out that difference. GPFS blocks are typically 1 megabyte in size when it comes to Hadoop, but actually can range between 16 kilobits and 16 megabytes. Now in big data, we want to deal with larger block sizes. So to kind of align with Hadoop and HDFS principles, the term GPFS chunk was invented, and a chunk is simply a group of blocks with a preference to be written across all available disks in a single node. We're going to take the 1 megabyte best practice for GPFS block size, and we're going to define the block group factor to be 128, and that will give us our 128 megabyte chunk size. Now, when we encounter a large file, like in this example, where it's 270 megabytes, that file will then be broken up into two 128 megabyte chunks, and any remainder will be only as required to allocate the remaining 14 megabyte chunk. The next term I'll cover is network shared disk, or simply NSD in short. And you'll see this term a lot in GPFS documentation. In this picture, what you're seeing is 4 nodes that are part of the GPFS cluster. So just like you would have a Hadoop cluster where they can all see HDFS file system, these 4 nodes can all see the GPFS file system, and this is locally mounted on /GPFS/Big Insights, for example. So wherever the data actually physically resides, each of these nodes, because they're a member of the cluster, can see all the files as if they were local. Now what's important to see here is that while there are 4 nodes, only 2 nodes actually have NSDs. Now when it comes to reading and writing data, only the 2 nodes in the middle will actually persist data to disk. Now in the Hadoop world, every disk is referred to an NSD. So just think of disk and NSD as being direct equivalents. And the nodes in the middle, if a data node has 12 disks, is simply said to have 12 NSDs. And a node that has at least 1 disk is referred to as an NSD server. And so for example, the 2 data nodes here are NSD servers. The management node or the app node, they have no NSDs attached. They're sometimes referred to as GPFS clients. Now in Hadoop, there is this notion of a name node, which manages the metadata of the files across the cluster. GPFS also has metadata, and I'll talk a little bit about its metadata strategy in a moment. Now for all intents and purposes, the metadata that GPFS tracks is very similar to the metadata that HDFS would track, but the strategies that it manages it are very different. Metadata would include things like file size, name, owner, last modified, quota information, inode information, access control list or security information, and so on. So as you can imagine, metadata is really vital to the file system's availability and integrity. So we would take extra care, just like the name node in HDFS, to take care of that data. The next term I'll cover is storage pool. And a storage pool is simply a collection of NSDs. Now there's always one default system pool. And so if I create a brand new GPFS cluster, I'll get this system pool and it will actually contain both metadata and data if I did nothing else. So in this picture, you can see I've got my two servers in the middle that are NSD servers, and I've got a single system pool with both metadata and data. And this is fine for small clusters. Now in Hadoop, we'll typically define more than just a system pool. On the left, what you see is management nodes that have disks dedicated to the task of storing metadata. And so you have the blue disks, which are NSDs assigned to the system pool. On the right, you'll see that there is a data pool with NSDs in them, and these will be used only for data. But that data's metadata will be stored in the system pool. Now we do have some best practices here, and if possible, what we want to do is have your metadata sitting on solid state disks for fast random access. The alternative is to have multiple disks that serve up metadata to keep up with the request rate of the workload. You might be tempted to put metadata disks across all available nodes. This can technically be done, but don't do it because this actually will reduce the availability of the cluster in the event of a failure, which I'll get into a little bit later. And further, you want to limit the number of metadata nodes to just one or two per rack. Now this picture is a small modification of the previous one, where we're showing 3 metadata disks. The objective is simply to show you that a disk can belong to any node, and any disk on any node can belong to any storage pool. Generally speaking, a storage pool is just about grouping disks that have similar roles or performance characteristics. So the metadata disks, which belong to the system pool, all have similar high performance SSD characteristics and similar access patterns, whereas the large capacity drives are traditional spindle disks. So there is no technical restriction for where metadata can reside. Now for resiliency of the metadata, each time metadata is created, GPFS will write the metadata across 3 different metadata drives. In this case, it makes sense for us to have those drives across 3 different nodes, so that if we lose a node, we still have metadata surviving on the 2 remaining nodes. Now let's talk about the 3x replication that HDFS is so well known for. GPFS also makes 3 copies of the data, but of course, making 3 copies of data alone is not enough to ensure that the data is resilient to failures. So in this picture, we've taken a data chunk and we've written it 3 times, but all on the same node. So this is not so useful. How can we do better? What we really want to do is make those 3 copies across 3 different nodes. And so GPFS has a mechanism for supporting this. So GPFS again has a very disk-oriented view of the world. How does it go about making sure that those 3 writes are written across different nodes? For that, we introduced the term failure group. And failure group simply means all the disks that failed at the same time. So if we're trying to protect against node level failure, what we would do is define the NSDs that are attached to a specific server as to be part of the same failure group. So in essence, a failure group represents all the NSDs that share a common point of failure. So extending this to a Hadoop example, where I have multiple nodes, what I want to do then is define one failure group per node in the very least. And so when GPFS decides to make 3 different writes, it's going to choose 3 different failure groups to make that write. And this is how it ensures that the data is protected. Now a failure group can be just a number. Failure group 1, failure group 2, failure group 3, but it can also be more than that, and I'll get into this in the next slide. Now you also see here there's an edge node. The edge node is part of the cluster and can see the file system logically, but it is not an NSD server. And so in this case, failure groups doesn't apply to the edge node. Now let's enhance this picture to include metadata. We can have our metadata on 3 different nodes. So when GPFS writes its metadata, it's going to choose metadata disks from 3 different failure groups. So now we're going to extend the concept of failure groups, and we'll see why this is necessary. Here's a picture of a rack where we've got an upper rack and a lower rack defined, and the network configuration is such that we can have a failure of half the rack and still continue working. So what we've done is we've taken the failure group concept of a single number and extended it for Hadoop. So failure group now can be a 3-part number as well, where the first number indicates the rack number, the second number represents position, upper or lower rack, and the third number represents a node number. Now the position number in the middle needs to be a 0 or 1 representing upper and lower. And if I have multiple racks with multiple upper and lower sections, I can express that with the failure group numbers. So GPFS will use failure group information to place copies of the data as far apart as possible. For example, failure group numbers that are different on the first position are the farthest apart because they denote that they're on different racks. When the number differs on the second number, it means that they're on the same rack but on a different upper and lower section. And finally, if the number is different on the third number, that just means we're writing to a different node. And so in this example, the first write goes to rack 1, lower section, node 12, and it's going to choose a second and third writes to rack number 2 and to an upper and a lower section. Now I should take a moment to talk about recovery from failures. If a node goes down and those disks become unavailable, it will take the data on that failed node and redistribute onto surviving nodes so that we reestablish the 3x copies. Now, how does GPFS differentiate between, say, a server reboot, which would temporarily make the node unavailable, versus a true server failure? Well, there are thresholds defined in the system, and by default, our best practice is to configure a delay of 40 minutes or 60 minutes, depending on whether it's metadata or regular data, before we start this restrike process. So this allows you to take down the node for a quick maintenance patch reboot without causing a restripe operation. So now let's look at the lowest level of detail of how we're going to configure our GPFS cluster. Let's say that I've got a node with 12 data disks, and those disks are available to us on /dev/SDC through SDK. Because all of these drives belong to the same node, and if that node goes down, all of them become unavailable, they're going to have the same failure group definition, in this case 101. So you see every drive has the failure group 101. Here I've added node 21, and node 21 has 2 disks, SDC and SDD. Now because this node 21 is on a second rack, on the upper rack, and is node 21, the failure group number is 2021 for both those disks. Similarly, for node 22, which is also part of the upper rack, has a failure group number of 2022. Now on the lower rack, I have nodes 30 and 31, and so you see that disks SDC and SDD on node 30 have the same failure group number, 2130. So when I create my GPFS cluster, I'm going to tell it this information about the disks and which servers they belong to through failure group definitions. So a stanza file is a convenient way to define all the disks and their attributes. The things we would define are things like failure group, the storage pool each disk belongs to, and usage, such as data only, metadata only, or data and metadata. So in this example, I have one management node and one data node. On the management node, I have a disk label called M1_disk1. That's simply a unique name to identify the disk. The device indicates where I would find the disk on the operating system. This servers clause indicates the server name. The usage will be metadata only, and the failure group is 100, and the pool is system pool. Now on node 1, we have 3 drives. We have N1 disk 1, and these are just labels again, N1 disk 2, N1 disk 3, and so these 3 disks are part of the pool called data, and their purpose is data only. Now this is a very simple cluster. Let's take a look at how this would look on a larger cluster. Here's an example with 2 management nodes and 9 data nodes. Now nodes 2 to 8 are going to be very similar, so we're just showing nodes 1 and 9. In this example, M1 and M2 each have one drive for metadata, and each of these drives are belonging to the system pool in red here. Now because these are two different nodes, M1, M2, the failure groups are different. And you notice that metadata only has a one-part failure group number, and that's by design. For node 1, we have 3 drives, and so you see that the failure group for those 3 drives are the same, 1, 0, 1. Their membership is to the data pool, and their purpose is the same, data only for all the 3 drives. Similarly, for node 9, you see that the failure group is just 119, and they're the same for all disks on this node, and these disks are part of the data pool. So I want to tell you this is pretty much as complicated as it gets when it comes to setting up our GPFS cluster. Let's take these concepts and apply them to single node, single rack, multi-rack configurations. So if we're in a single node configuration, and you might have this for demonstration or learning purposes, you can easily enable this by adding an additional virtual disk to an existing virtual machine. And so the first disk that you have on that virtual machine for one node will be used to boot the operating system. You can add a virtual disk to the environment, and that virtual disk can be used for GPFS. Now, because your resources are limited in this environment, replication factor will be set to 1 automatically, and the metadata and the data will reside in a single system pool. Now here's a common starter configuration of, say, 5 nodes. So here you see that each of the nodes are defined as their own failure group. So I have 5 failure groups to match with the 5 nodes. Now I do want to have metadata written across 3 different failure groups. So what I can do is take one of the disks on the data node and assign it to the role of metadata. And so there's nothing wrong with putting an SSD drive in my data node and making it part of the system pool, but in a different failure group. And so I've got my metadata across 3 different failure groups, and I've got my data across 3 different failure groups. Now let's look at the failure group definitions. For these 3 drives in blue, those are my system pool disks. And so they'll have failure groups 100, 101, and 102. Remember that metadata disks don't have 3-part failure group numbers. It's just a single digit number. In my FPO data pool, all the disks on data node 1 will have failure group 103. All the disks in data node 2 will have failure group 104, and all the disks in data node 3 will have 105. So here's a bigger example where I've got 3 management nodes and 18 data nodes. So there is a management node here that you don't see because they didn't have space to fit it, but these NSDs will be labeled as being part of system pool and failure group 101, 102, 103, one for each disk. Now for my data nodes, I have data nodes 1 through data node 9, which are on the upper rack. And so what we'll have for those drives are failure groups 101 for data node 1, 102 for all the disks on data node 2, and 109 for disks on data node 9. Now because data nodes 10 through 18 are on the lower rack, the middle number will change for those NSDs. Now here's how things look when we have 2 racks. I should also mention that having upper and lower racks are completely optional in GPFS. Now in this picture, look at how I've spread out my metadata. I've got metadata disks on rack 1 upper, I've got metadata disks on rack 1 lower, and metadata disks on rack 2 upper. This will ensure that if I have a partial rack failure or complete rack failure, that my metadata survives. And everything else sort of remains the same in terms of how we define failure groups. We've got node level failure group, upper and lower rack failure group, and we have now rack level failure group. And finally, this is how things look in a multi-rack configuration. So that first number here will be 1, 2, or 3. The second number will indicate upper or lower rack, and the third number will be the actual node number. Now, because I've got lots of nodes, what I can do is have my metadata nodes spread across the 3 racks. This will be good for performance and resiliency. Finally, I want to mention this one best practice. Now, the default behavior of GPFS for a node that's receiving data is to see if it can write data locally first. And this is for performance reasons. Now, imagine what would happen then if I were to ingest a lot of data through a data node which had local disk. We would get imbalance because all the data would always write its first copy to itself before distributing the second copy to other nodes. So, as a best practice, what we should do is ingest data through an edge node. Now, if you ingest data through an edge node, that is a node that does not have its own local disks, GPFS will then automatically distribute the data evenly across the cluster because it has no opportunity to write to itself first. And this actually aligns with a best practice where all our Hadoop data nodes are on a local private network that is not exposed to the outside. And we have management nodes or edge nodes that are entry points into the cluster. And so if you follow the IBM best practices for building Hadoop clusters, this is automatically taken care of. So in summary, we cover three key terms that are really important for GPFS. The first is NSD, which simply means a disk, network storage device. We learned about storage pools, which helps us define to GPFS groups of disks with a similar role. We also learned about failure groups, which helps GPFS decide where to place its data to avoid common points of failure.